Up until this point, we've been assuming the chemical reactors we've been analyzing are isothermal. And we're not, starting in chapter 8, and this is this book, The Elements of Chemical Reaction Engineering, and I have the 4th edition. So starting in chapter 8, we're not necessarily making that assumption anymore. And so we'll start seeing temperature changes through the reactor, heat exchanges, energy exchanges. So basically we need to come up with a way to take into account these temperature differences, because if you remember, your reaction rate constant is highly dependent on temperature. So if your temperature is changing, your rate of reaction can also change. So in this video, I just wanted to point out that I wanted to point out this table. It's table 8-1, and it's called Energy Balances of Common Reactors, and it's on page 476 in the book I have that I just showed you. And so anyway, if you are doing a problem where you need to take into account temperature, you will most likely be able to just pull an equation off this table. But having said that, I think that it can be kind of confusing to know which equation you need to use, and so I think that it's really helpful to understand how these equations are derived, because then you know, first of all, if it applies to the reactor you're analyzing, and second, you know what assumptions were made for the particular equation, so then you know if it applies in your situation, because you don't want to be using an equation like maybe your reactor is. So one assumption that almost all of these make in this table is that there's no work, like the work is 0. And in a lot of chemical reactions, that's the case, that it is 0, but say you have a reactor that has a highly viscous fluid in it or something like that, so then your work might not be 0, like you would need to account for it, and so then you can't just pull one of these equations because it would be wrong. And in this video, I'm basically going to derive the steady state energy balance, like the really general case. And then in subsequent videos, I'm going to show you how that applies to adiabatic operation, which would be the first equation on that table. And then I might do an example with that. And then I'm going to look at CSTR also. And then I'm going to go through the derivations for the equations with heat exchanges. And for both the for the tube reactors, which is a PBR and a PFR, and then for a CSTR. And then I'm probably also going to do a video specifically on CSTRs and determining, well, heat effects in CSTRs, and talk briefly about runaway reactions. So first of all, one thing to keep in mind with as you start thinking about applying heat effects in reactors, first of all, your design equations, rate laws, and stoichiometry are still the same. The only difference is how your design equation is evaluated, because now you have another equation for heat effects. And you'll see as you go through that depending on what kind of heat effects you have, you'll either end up with a coupled differential equation or an algebraic expression. And so basically, in order to solve these problems, you need a relationship between x and t, so the conversion and temperature. And so that's where the energy balance comes in. So I'm just going to write that. So to do an energy balance, you start with the first law of thermodynamics. So so thinking about reactors, we want to apply this for an open system, and the reason why is because we have fluid flowing in and out, so it's open. And so if we do that, we have the change of the energy in the system with time is equal to Q minus W, and I'll explain what all these are in a minute, plus flow in multiplied by energy in minus flow out multiplied by energy out. And so then this is the rate of accumulation of energy in the system with time. So rate of accumulation of energy. This is the rate of heat flow to the system from surroundings. Rate of heat flow from surroundings. And that, I mean, that's either in or out. This is the work done by the system on the surroundings. This is the rate of energy added by mass flow in. And this is the rate of energy added by mass flow out. So it's kind of the same as this, only this one's in, this one's out. And also, typical units for this would be, say, joules per second. Just say, you know. And so the first thing I want to look at is the work term. Because we have this equation, but it's not very useful in this form. So I'm just going to go over here, actually. So for work, first of all, you have flow work, which gets the mass into and out of the system, and then you can also have shaft work. I'm sure you know this from physics, but just in case for a broad overview. And the shaft work could be from a stirrer, say in a CSTR, or a turbine in a PFR. And so for the work, first of all, we're going to assume that there's no shear stresses. So then this would equal minus, well, sum of I to n, Fi P Vi in, plus I equals 1 to n, this is the sum, Fi P Vi, and this is out, and then plus shaft work. So first of all, this is just to make sure you know what these are. This is pressure. And this V with this squiggle over it is specific molar volume. So just real quick, I wanted to look at the units of this. So Fi P Vi, and the units, so first of all, this is the molar flow rate, so moles per second multiplied by pressure. I'm just going to say Newton per meter squared. And then the specific molar volume is mass, or actually, sorry, it's a volume divided by moles. And so then you end up with, that cancels, so you end up with the Newton meter per second. And this is equal to joules per second, which is equal to watts. Now what I want to do is combine this into here. And so I'm going to erase some stuff to do that real quick. Is equal to Q minus the shaft work plus, and then I kind of combine these two sums. So for the first one I had the sum of, if you remember, I had the sum of energy in with the flow, and then for the work I had so this was in this first equation, and then in the work equation I had this sum of flow P specific molar volume. And so in this equation I'm combining these terms. So doing that, I have the sum of Fi EI plus P VI, and this is in, minus Fi EI plus P VI, and this is out. This EI is the sum of internal energy, so EI sum of internal energy, which is written as UI, the kinetic energy, so UI squared over 2, the potential energy, so GZI, and others such as electric or magnetic energy. So just remember that this is a sum of all the possible energies that could be in the system. So if we rewrite that, EI is equal to UI plus UI squared over 2 plus GZI plus others. And so in chemical reactors, and this is one of those assumptions that I'm talking about, where if this doesn't apply to your particular reactor, then you need to go back and account for this. But in most cases, this is usually negligible. So usually in chemical reactors. So then you can say that EI is only equal to the internal energy. So then if we go back to here and we plug in UI for EI, so we have, I'm just going to go over here, so we have UI, or sorry, yeah, so if we take this term, so EI plus P VI, and we say that this is equal to UI plus P VI. This is the enthalpy, so this is equal to HI. And the units for this are joules per moles of I, or this could also be BTU per pound mole. So then if we substitute enthalpy in for this, we can rewrite this equation in a slightly simpler form, and I'm going to erase some stuff real quick and do that. Alright, so plugging in enthalpy, we can rewrite this equation as the energy change in the system with time is equal to Q minus shaft work plus the sum of Fi enthalpy in minus the sum of Fi enthalpy out. So then this is the equation that you manipulate to apply to different reactor types. And so the first thing I want to do is derive the steady state energy balance from this equation. So basically put it in a more usable form. And so first of all, before we even start, I'm assuming steady state. So this is 0. And then we want to rewrite this equation in terms of the heats of reactions. So heats of reactions. So first of all, I'm going to assume that I have the following reactions. So assume that we have A plus B over A, B, to C over A, C, plus D over A, D. Then we can rewrite these as, so H I naught F I naught is equal to H A naught F A naught plus H B naught F B naught plus H C naught F C naught plus H D naught F D naught plus, and then we also need a term for inerts because there might be inerts involved that wouldn't be written in this equation. So H I naught F I naught. And then we can do the same thing for, so this would be in because that's initial. So, and then this is this term. So F I is equal to H A F A plus H B F B plus H C F C plus H D F D plus H I F I. And then we want to express these molar flow rates in terms of conversion. So we can do that. You should remember that Fi is equal to Fa naught theta I plus Vi x. So applying this, we get that Fa is equal to Fa naught 1 minus x, Fb is equal to Fa naught theta b minus b over ax, Fc is equal to Fa naught theta c plus c over ax, Fd is equal to Fa naught theta d plus d over ax, and F inert is equal to theta inert Fa naught. And then just to remind you, theta I is equal to Fi naught over Fa naught. So then if we substitute these in, I'm basically putting these into these two equations and then substituting these back into here. So that one goes in there, this one goes in here. And I'm not going to go through all the algebra involved because it's pretty long, but if you do that, you get the sum. So I'll just rewrite this. The sum of the enthalpy initial Fi naught minus the sum of Fi Hi is equal to Fa naught multiplied by H A naught minus HA plus HB naught minus HB theta B plus HC naught minus HC multiplied by theta C plus HD naught minus HD multiplied by theta D plus HD I naught minus hi multiplied by theta I. And then this is all, I think I'm going to run out of room, but this is all minus d over a hd plus c over a hc minus b over a hb minus ha fa naught x. And this particular term is equal to the heat of reaction T. Because if you remember, see, I'll write this up here. So the heat of reaction, and this is the temperature at the outlet of the system, is equal to d over a h dt plus c over a hct minus b over a hbt minus h a t. And that's what we have down here. So we can plug in the heat of reaction for that, and I'm going to also rewrite these back in the summation form just to save room. So I'm going to erase some stuff and do that. So rewriting the equation with using the equation I just had and plugging in the heat of reaction, and then also rewriting that expanded FI/HI in summation form, we get Q minus shaft work plus FA naught, and this is the sum of theta I H I naught minus HI minus the heat of reaction T FA naught X is equal to 0. This is technically the steady state energy balance, but I want to take this a step further by showing you how the enthalpies are calculated. So HI is equal to the enthalpy at some reference temperature. Usually you would look this up on a table, plus the change in enthalpy when the temperature is changed. And so if we assume no phase change, then we can say that this term, the change in enthalpy with the change in temperature, is equal to the integral of temperature 1 to temperature 2, the heat capacity dt. And this heat capacity, the units of that are joules per mole of I Kelvin. And just remember this, you can only apply this equation if there's no phase change. If you have a phase change, you have to use a different, more involved equation. So just remember that's one of the assumptions. So no phase change. So doing that, you get that H, or the enthalpy, is equal to the reference enthalpy plus, and then this would go from the reference temperature to temperature, C Pi dt. And then we can integrate this, and when we integrate that, in this case, we're assuming constant heat capacity, but that's another thing. It might not always be constant, so you just want to keep that in mind when you're working through problems. So if we assume constant heat capacity, then we get the, so then this, I'm going to actually go over here, we get that this term hi minus hi naught, so this is equal to hi at some reference temperature plus this integral of the reference temperature to T, Cpi dt, minus hi at some reference temperature plus the reference temperature to Ti naught Cpi dt. And then this is equal to the reference temperature plus Cpi T minus Tr minus this enthalpy at this reference temperature again, minus Cpi Ti naught minus Tr. And then these will cancel out, this will cancel out, and you're left with Cpi T minus Ti naught. And so then you can plug this into here, and I just want to reiterate that in order to get this, we're assuming that your heat capacity is constant, and we're also assuming that there's no phase change. So if you have either of those two things, this won't apply. So just keep that in mind. So I'm going to erase everything and then rewrite this equation with this plugged in for this. Okay, so rewriting this equation, I have Q minus the shaft work minus Fa naught, the sum of theta I Cpi T minus Ti naught minus the heat of reaction T Fa naught X is equal to 0. I want to come up with a relation for the heat of reaction for this, so relate the heat of reaction at this temperature and the heat of reaction at some reference temperature, and delta C sub P. So first of all, I already had this written down, but I'll try it again. We already know that the heat of reaction at this particular temperature, whatever temperature that is equal to d over A H dt plus C over A H Ct minus B over A H Bt minus HA T. And we also know that the enthalpy is equal to the enthalpy at some reference temperature plus this integration T Cpi dt, and this was equal to the enthalpy at this reference temperature plus Cpi T minus T reference. We can say the heat of reaction at this reference temperature is equal to d over A HD TR plus C over A HC TR minus B over A HB TR minus HA TR. And then this is the heat of reaction at this reference temperature. And then we can also expand this out. So if we do that, we have d over a c sub p d plus c over a c sub p c minus b over a c sub p b minus c sub p a. And then this would all be multiplied by t minus t reference. And so you should recognize this as c. This is delta c sub p. So then taking this and this, we can rewrite delta heat of reaction T is equal to the delta heat of reaction at some reference temperature plus delta C sub P T minus TR. So then you can plug this into here, and the reason why this is useful is because this heat of reaction at this reference temperature, that's tabulated at 25 degrees C for lots of compounds. You can find that probably online. You can find it in Perry's handbook or the Handbook of Chemistry and Physics. So that's why this is having your equation in terms of the heat of reaction at a reference temperature is more useful than having it in terms of whatever the output temperature of your reactor is. So I'm just going to erase some stuff real quick and then write down the final equation. So the steady state energy balance, Q minus shaft work minus FA naught sum theta I CPI T minus TI naught minus the heat of reaction at some reference temperature plus delta C sub P T minus T reference. This is multiplied by FA naught X is equal to 0. So this is the steady state energy balance. And I just want to quickly summarize the assumptions we made for this. So assumptions. First of all, we assumed steady state. We assumed that it was well mixed. We assumed that your kinetic, well, I'm just going to say I'll write kinetic, potential, electric, magnetic energy approximately 0 in this system. Let's see, we assumed that the partial molal enthalpies were equal to the molal enthalpies of pure components. We assumed no phase change. And we assumed that the heat capacity was constant. I think that was most of it. So I highly recommend going through this derivation on your own and go through all the algebra, and because I mean this derivation is in the book. This is the first section of chapter 8, and I find it really helpful to go through and write down the equations and actually go through the math versus just reading it. And then also when you have equations, make sure that you know what all the assumptions are, and that should help you a lot.